So yeah,
They make a cool noise.
guys, I only need one person talking at a time. So they make a cool noise if what? All right, they make a cool noise when you bounce them together. They won't. Okay, you can't get them to push together. Okay. All right, there's magic sand that you can put it in that the magnets will collect all of it. The field goes like this. All right. Right? That's kind of what I was thinking. All right, I'm going to write that one down. So magnetism, second grade understanding. We've got, if you're Marvin, a general shape of the field. General shape of the field is something like, and I can't really duplicate the sound he made. Opposites attract. And based on what Mackenzie was saying, like poles repel because you can't get them to stick together. Like poles repel. All right, were there any other ideas that we can put down there based on something a second grader could tell me? Black magic. All right, so most of the magnets that you guys would have encountered as a second grader were what we would call permanent magnets. There are magnets that had one end that was probably labeled as N, one end labeled as S, and they all were made of one of three different substances. So all magnets contain, all permanent magnets, thank you. All permanent magnets contain either iron, cobalt, or nickel. Those are the nickel, neodymium, nickel, neodymium. Neodymium exists in there to amplify the field that nickel actually holds. Neodymium on its own, you're not going to cut it. Okay? So all permanent magnets contain iron, nickel, or cobalt. And these are the only elements that have electrons that have what we call unpaired magnetic spin. You can have any one of these be a magnet. Yeah. All right. These are the only elements with unpaired electron magnetic spin. No, it is not. Okay, so everybody I'm sure has seen the really bad Indiana Jones movie that was made a few years ago, where they can show that pennies were attracted to the magnets, and they're like, but it's not magnetic. No? Yes? Okay. Yeah, crystal skull. Okay, so regardless, he points out that copper isn't magnetic and shouldn't be attracted to this object. Okay, so iron, nickel, cobalt are three elements. However, that does not mean that all iron, nickel, and cobalt are always magnetic. In order for one of these objects to be magnetic, we need for them to have their domains aligned. So this next piece here is domain theory. So if we take a magnet and we label one end as its N pole, one as its S pole, we can take a compass and we can map out the magnetic field around that object. So I'm going to remove that real quick. We can see that the red pole of my compass is pointing in general towards the north, which is towards me. Is that better? Where the N is actually under the red? Okay. So that means that the red pole here is an N pole magnet. Okay. So I'm going to go ahead and place this here. If the red end was an N pole magnet and this end is an N pole magnet, that means, hey, like poles repel, so this is being pushed away. Okay, I'm going to redraw this over here. I'm going to keep drawing this here. And evidently this entire side is an S-pole, not just that one end. All right, so evidently my magnet is shaped has a magnetic field that's shaped a little bit like this. All right, where have we seen drawings like this before? Electric fields, it's field forces, correct? So magnets create magnetic fields, much like electric charges create electric fields, or mass creates a gravitational field. So first of all, magnetism is a field force. Is a field force. Okay. For the last field force that we talked about, we had 3 rules for actually drawing the electric fields. What were those 3 rules? All right, so lines couldn't cross, and field lines came out of a positive charge or started at infinity. They ended at a negative charge or infinity. So lines can't cross. Domain theory, we're going to get to this. I mean, I suppose, but oh boy. So lines cannot cross, and lines start. She is. And all right. So we've got lines can't cross. Lines start at N, end at S. Notice there's no infinity option. Okay, we'll come back to that. What was the third rule for drawing electric field lines? All right, yeah. So the magnitude of the electric field we said could be represented by how many lines there were, by the opacity of the arrows we were looking at, but it somehow had to be represented there. So field line numbers or opacity represent the strength of the field. All right. So building on a little bit more of this, lines start at N poles and S poles and not infinity. This is because while we have electric charges that we can have just a positive charge, it's a proton. We have just a negative charge, it's an electron. We don't have something that's just an N pole or just an S pole. This is because magnetism is more like a direction than it is like an individual charge. When we talk about individual piece of a magnet, we could consider this magnet to be broken down into a whole bunch of little mini magnets. Each of those mini magnets is what we would call a domain. A domain is made up of tens of thousands, hundreds of thousands of atoms, each of which has its own magnetic spin. Within an individual domain, all of those atoms will have the same magnetic spin. So if I would say they all had spin in this direction, they would all be creating magnetic field directed in this fashion. If I have a chunk of domains that are not all in agreement with each other, within the domain, the magnetic spin will still be aligned. However, compared to nearby domains, they will be canceling each other out. So individual domains, meaning groups of tens of thousands or hundreds of thousands of atoms, share the same magnetic spin. Within domain, groups of atoms share the same magnetic spin. groups of tens of thousands or hundreds of thousands of atoms. Okay? If they've got the same spin and all of those domains align, they create a magnet. If they have different spin, those domains will cancel out and they create a portion that is non-magnetic. So this would be a non-magnetic material. I'll get to that in a second, I think. And this would be a group that is magnetic. Because the domains are all aligned and they all agree with each other here versus they don't agree with each other here. Yeah. No, see how I've kind of got these like not in grid fashion but kind of randomly chunked? Yeah, that was intentional. They do kind of group themselves. Does that answer your question there? Okay. Yeah. No, this is not some artificial thing that we do. It's something that they just naturally tend towards. Okay. An individual domain is caused by the magnetic spin of the electrons. Because we talk about it as spin, what we're really looking at is we could have motion forward or motion backwards. Unlike a positive charge or negative charge, which is simply a group of quarks in certain combinations, we're now looking at something that's moving. And anytime you have something in motion, we have forwards and backwards. Therefore, we always have N-pole and S-pole. You can't separate one from the other because you can't have one direction without the other. Because I fail English courses repeatedly. No. No. So let's see here. Magnetic spin is treated as a direction. Causing N poles to always pair with S poles. With S poles. Yeah. So, creating a magnet. All right, so first one that we've obviously got is the introduction of kinetic energy to a magnetic or possibly magnetic material through violent vibrations while in the presence of another magnetic field. So violent vibrations. No. All right, the next one. Marvin already pointed this one out. We could just heat this up. It can have kinetic energy through a different method. If I can get these things glowing red hot in a magnetic field, the domains will start to align. So,
Would that eliminate the south pole? Or the,
no, because you still have forward and backwards. Yeah, you can't. Yeah. So here I've got thermal energy in a magnetic field. All right. So I've got a bin of these small compasses where they're not very strong permanent magnets. Some of them are no longer oriented the correct way. Some of them have the white arrow as pointing north because they've spent too much time nearby another magnet in the drawer and they've been caused to flip. So long durations of time in the presence of a magnetic field will also cause things to pick up magnetic properties. So long durations of time in a magnetic field.
Is that why, like,
No, we have no idea why that happens.
okay.
And I'm not just saying I have no idea. Literally, we as humans have no idea why that happens. Okay? All right. So I've got three methods, guys. Three methods for creating a permanent magnet. This last one was the first one really recognized by us, and it is largely believed that Chinese were the first to find permanent magnets. as lodestones, which are basically iron ore that had trapped the magnetic field of Earth because they sat in the same spot for long enough. Okay?
So when we mine iron ore,
It can be magnetic already, yeah. All right. So looking at this list of things, anybody see a general trend? Energy. And you need another magnetic field here. So this kind of starts to create a chicken and the egg scenario. So in this scenario, the magnetic field that comes first is the Earth. So Earth has an electromagnet. So we've got geomagnetism here. All right. So drawing out the magnetic field of the Earth, this direction is north, this direction is south. I can take compass readings, and the end pole of my compass points that way all the time. And S. So if the end pole of my compass points that way, what kind of magnet has to be up at the North Pole? An S pole. Because it's attracted to that spot, right? So a couple of things about Earth's magnetic field. First of all, there's an S magnetic pole near geographic north and an N magnetic pole near geographic south. So some of you may have caught on to the fact that I use N and S and not north and south. That's because I reserved north and south for geographic designations and N and S for magnetic designations. That way, if I'm talking about north, we know I'm talking about that way, versus if I'm talking about an N pole, I'm talking about what pole of the magnet we're actually discussing. That's that way. All right? Next thing about Earth's magnetic field. North geographic and the S pole are not at the same spot. They're off by, if I remember right, it's like 8 degrees. Never. So, yeah, I'll get to that stuff in a second. So, guys, Earth's magnetic field, we have field lines extending out from the N pole into the S pole. Okay? And why do they exist? So the initial response I get frequently is that, well, what's Earth's core? Iron. Iron and nickel. Hey, iron and nickel is a magnet. We've got a giant magnet here. So we didn't solve the problem then. What caused Earth's magnetic field? Yeah, we can start to try to go with the sun, but the sun's magnetic field is changing rapidly all the time. Convection cells within the sun and solar flares are very common, and we wouldn't be able to maintain a static field long enough for Earth to actually steal this magnetic field. Wow, that was a lot of hands shooting up at once. I'm starting left and moving right. What? I'll get to why it had to be Earth magnetic before the dinosaurs. Not a thing. Convection within the Earth, go in there. Connor's moved far enough left that he's next.
What is this? It's a celestial pool.
Yeah. That's same as
That's
geographic.
not magnetism?
Nope. Gravity. No. 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 All right. So, guys, the core of the Earth doesn't actually matter. The core of the Earth is just kind of there. It may help enhance this magnetic field, but what matters, as Forrest pointed out, is convection within the mantle. So within the mantle, we have all sorts of magma. Convecting, meaning hot stuff rising, cool stuff falling, right? Well, when we talk about magma, it's hot enough at this point where it's ionized. So we're now moving large groups of charged material, and motion of electric charge creates magnetic fields. So motion of electric charge.
So it's similar domain.
in a way, but more less static, more changing. Motion of electric charge causes magnetism. Yeah, simply because it's so hot. Right. So, and convection of ionized magma or material, I'm getting there, causes magnetic field. This is Mr. Carney. Talking about Earth's magnetic field and the dinosaurs and Mars. So convection within the Earth causes this magnetic field, and we actually need the magnetic field. Why does we need Earth's magnetic field for survival? Okay, so without the Earth's magnetic field, cosmic radiation, solar radiation, gamma rays specifically, big solar flares, hey guys, I need you to stop talking. All of these things would easily wipe out life on Earth. Okay, beyond just gamma radiation and that content, we would be talking about these rays stripping away Earth's atmosphere. So without the magnetic field first, we can't even get the dinosaurs to develop. So we take a look at a comparison between Earth and Mars. Mars is a little bit smaller than Earth, correct? Think about two baked potatoes. You got a larger one, you got a smaller one. Which one's going to cool down first? Smaller one. Smaller one's going to have the insides cool down first because there's less insulation. Planets work the same way. Because Mars is smaller, it cooled down faster. Because it cooled down faster, convection slowed. Because convection slowed, fewer or lower magnetic fields, less magnetic field, more of its atmosphere that it originally had was stripped away by the sun's radiation. So what potentially could have turned into another developed habitable planet where we've got life existing, or we could even go there and possibly live, we don't. We instead have something where there's less atmosphere, it's too cold, and the top of the surface gets more radiation than we do. Yes, Alan. In the, I believe it was 1940s/50s, one of the things that we started doing was mapping the Earth's sea floor. We started mapping the sea floor following World War II because World War II was the first one that saw the use of submarines. Prior to that, we didn't really care what was beneath the Earth's surface. Anything military that we needed to know about, you could see coming. But now with the invention of submarines and sonar, we needed to know exactly what was down there. Where could submarines hide? What would the seafloor look like at different locations? Where could we tell if there's an anomaly? So it was militaristically motivated. And what we found when we lowered detectors and sensors down towards the seafloor was that as you approach the mid-ocean ridge, what's at the mid-ocean ridge? What's that do? Yeah, Mariana Trench. We've got the outcoming of all sorts of hot stuff. And that's where the Kraken evidently lives. Okay, so new seafloor is continuously being made there. We have magma, hot stuff that contains iron coming out and cooling. Well, wait, we've got iron, we've got Earth's magnetic field, we've got a permanent magnet here. The Earth's seafloor is a permanent magnet. The entire seafloor is a magnet. And what we found is that as you move out from the Earth's seafloor, you can measure the magnitude and direction of that magnetic field, and it points to the north. However, as you move further out, we find strips of the Earth's seafloor that point in the opposite direction. And we find them in equal bands on opposite sides of the mid-ocean ridge. So we find bands that point north, then bands that point south, then bands that point north. And based on calculations about how quickly seafloor is created and the width of these bands, we show that on average, once every million years, Earth's magnetic poles flip. If you want to phrase it that way, yeah, it does. That's how we get continental drift, right? All right. So when we've got these bands being created, these are locking in place Earth's magnetic field at the time when this portion of the seafloor is created. So we're seeing we project that the same thing must have happened with all these other bands as we move out, meaning that every million years or so we get a flipping of the magnetic poles, and we are currently 10 million years overdue. A pole flipping. However, yes. However, However, we also find that there are studies currently being done that believe that the Earth's poles are actually starting their flipping process. It's not a flip, it's a migration from what we understand, which obviously doesn't have any immediate impacts. However, we won't have northern and southern lights. At some point, we'll have those lights occurring immediately over top of like land masses where people live, right? We'll have the North Dakota lights. That'll be kind of cool. No. Yeah, that just happens to be where they are right now. They will migrate to the opposite side based on what history shows us. But before anyone asks me why they flip, yeah, we have no idea.
What will happen when they flip?
So, as best we can tell, what will happen when they flip? North will be south, south will be north. Animals that use actual like magnetic fields to migrate will it will slowly adjust based on evolutionary tracks. But beyond that, prior to humans, which haven't seen a magnetic pole flip in our existence, no, we found the crater from the asteroid that did that. It's off the Yucatan Peninsula in Central America.